Hey guys, today we're going to learn about residuals, residual plots, and influential points. Let's get started. Remember when we've talked about the last couple of videos that a residual is simply error. It's the vertical deviation between the observations that we actually have and the predicted values that you would find for y on the least squares regression line. So if we had our prediction line, all of our residuals or our errors are these vertical deviations like we calculated in the video from last class. The sum of the residuals for a least squares regression line will always be 0. That means we will have the same overall total positive error and negative error for my scatter plot compared to my prediction equation. When we calculate the residual or the error, it is always our actual values minus our predicted values. So what we observed from our data minus what we expected. So our residuals are calculated by taking each y value minus the y hat, which is the predicted y value. So again, we're looking at actual y's minus predicted y's. When we look at our residuals and calculate those for each of the data points in our data set, we can actually create what is known as a residual plot. A residual plot is a scatter plot, typically of the x values in our data set plotted against the residuals, or the errors. The residuals can be graphed against other statistics besides our x value, and we'll look at that when we take a look at a couple of residual plots. The purpose for a residual plot is to tell us if a linear relationship really does exist or is appropriate between our two variables. When we look at the residual plot, if there is no pattern that exists between the points, it is a random scattering of points, then we say the association is linear. If we notice a pattern in our residual plot, that tells us that our relationship is not linear, and what we'll talk about in a couple of classes is what we can do to transform the data so that a linear relationship really is appropriate. Let's take a look at a side-by-side comparison of two residual plots. The plot on the left shows a random pattern in the residuals. Notice we're plotting the x's against the residuals, which means every point in my plot is an actual ordered pair of the x value from our data set and the residual calculated at that particular x value. When the residual plot is random and there is no pattern, it tells me the linear relationship exists between my x and y variables. In the second residual plot, there is very clearly a pattern in my errors or a pattern in my residuals. That is evidence of a nonlinear pattern, and additional steps must be taken to transform that data to be linear. But we're going to talk about that in a couple of class periods. Let's take a look at examples so we can go through calculating residuals and also talking about our coefficient of determination. I have a data set here for several patients that had knee surgery, and one of the measures of success for knee surgery is the post-surgical range of motion for the knee joint. So if you see, this is a number of different patients. We've plotted the x-axis as their age and the y-axis as their range of motion following knee joint or knee dislocation surgery. We have a a scatter plot that we can create for x and y values. We're going to go through now and create our y hat, or our prediction equation, just like we did last class. You may want to pause the video now, grab a calculator, and do your linear regression model and create your least squares regression line or your y hat prediction equation. The y hat prediction equation is 107.583 plus 0.870976x. Or in terms of our variables, it's our range of motion, hat, equals 107.583 plus 0.870976 times the age. The age is our explanatory variable, and the range of motion is the variable that we're measuring, or our response variable. Well, if we take a look at the y hat value, we can actually, or y hat equation, we can create a y hat or predicted y value for each of these x points. So we're going to take our age or our x value, plug it into our equation, and get a y hat or predicted y for every one of these data points. I will create a second video that will show you how to do this on your TI Inspire calculator in case you don't already know how. Right now, we're going to actually plug in our y hat values, and we're going to fill in the chart here for y hat. These are our predicted y's. And then we're also going to calculate a residual for every data point or an error, which is the y minus y hat values. You will take a look at a scatter plot now, and we're going to actually do what is known as a residual plot. To do that, when we go to our Data and Statistics page and we click for our variables, once you've calculated a least squares regression line, you will notice there are new variables that appear as your choices when you click on the X and the Y axis. So here we've taken a look at a scatter plot that actually shows us plotting our X's against our residuals. When you do this on your calculator, these may be called stat.resid, and you're going to simply create a scatter plot where your x-axis are your traditional x values and your y-axis are your residuals. That's how we calculate a residual plot. This allows us to answer the question, is there a linear relationship between age and range of motion? Because that relationship might be quadratic, cubic, or exponential. Well, if we look at this residual plot, since there is no discernible pattern in our residual plot, that means there is a linear relationship between age and range of motion. So a linear relationship is appropriate. On an earlier slide, we said that our residual plots could be plotted against a number of different variables. Here we're going to look at a side-by-side comparison. The graph on the left are my x values for my original data set plotted against my residuals. On the graph on the right, it is my y hats along the x-axis plotted against the residuals. Now typically it's pretty easy for us to create an x plot against our residuals, but notice the residual plots are the same, no matter whether we plotted our residuals against our x or our y hat values. Once we know that a linear relationship is appropriate, we can calculate what is known as our coefficient of determination. Remember, our correlation coefficient was called R, but R squared is called our coefficient of determination. The coefficient of determination gives us the proportion or percent of variation in the y values that can be attributed or explained by the linear relationship between the x and y values. Now that's a lot to understand, and I'm going to walk you through a complete explanation of exactly what a coefficient of determination is. Now, the coefficient of determination, or R squared, remains the same no matter which variable is labeled x. Just like with our R value, we could switch our input and output and get the same R. We can also switch the input and the output and get the same R squared value. So back to our knee surgery data, we have age and range of motion. So I'm going to walk you through how to calculate and what it really means to calculate an R squared value. So let's say just for a second you needed to have a surgery for your knee dislocation. And you called the doctor's office and you said, look, I just need to know on average what kind of range of motion could I expect to see after this surgery. Well, if the doctor doesn't know your age or anything about you, their best guess would simply be to take all the Y values for the surgeries they've done and calculate Y bar, or the mean. So if your doctor calculated the sample mean for all their surgeries, they might be able to tell you, on average, you should expect 130 degrees of flex. Well, how close are all of these individuals that the doctor did surgery on to that Y bar, or that average value? Well, if I take a look at the scatter plot, and this little yellow plot here, these are my individual data points that were graphed. And each of these vertical lines represents the error between what we actually saw and what we would have predicted as a range of motion using Y bar. Well, if I wanted to figure out all of the residuals, so I would take each y value minus the y bar value. Remember, we square them to make them positive and we add them up. We could get what is known as the sum of the squared errors or the sum of the squared residuals. And that's this number here. This number represents the sum of the squared errors or residuals if I use the mean of y. Now, I'm not going to ask you to calculate that directly, although if you understand that this is each y minus the mean of the y's, take those values and square them and add them up, we could use our calculator if we needed to do that calculation. What's really important here is I want you to take a look at the size of this value, and then I'm going to use that to kind of explain what the coefficient of determination does. Now, instead of just giving you an average y value, what would be more important is if the doctor actually asked you maybe your age. And the doctor could then use a y hat, or a predicted equation that shows the relationship between x and y. This is our least squares regression line, or our line of best fit. If you look at this plot, now we've plotted that y hat line, that prediction, and now we can look at how far off our prediction was for each of these individual values for x. Well, now if I take your age into consideration, I'm going to get an overall better guess for you using y hat than I did for y bar. But we could do the same thing here. We could take each actual value for y, but this time we're going to subtract the y hat. We're going to look at the actual minus the predicted, and we're going to square those values to make them positive, and we're going to add them up. So now if we look at the sum of the squared errors using y hat instead of y bar, will you notice that there's less error overall? Well, by what percent did my error go down? We can actually calculate this. We can take the difference in the errors using the sum of the squared error for y bar minus the sum of the squared error for y hat, and we can see how much that went down, and then we divide by our original sum of the squared errors for y bar. This allows us to calculate by what percent the sum of the squared error went down when we went from the overall average model to the regression on X model, and we get 30.62%. Well, what does that tell me? This is our R squared value. You've just found the coefficient of determination. If we look at a picture, we can see that the amount of error here that I would then square and add up using my y bar is greater than the amount of error that I would have here using my y hat. Knowing x and the relationship between x and y, which is taken into consideration in my prediction model, allowed me to decrease the error. In fact, this R squared value can be interpreted as the variability in y that is explained by the linear relationship between x and y. In other words, knowing your age allowed me to better predict your y value or your outcome. So this is how we would interpret that R squared value. We would say approximately 30.6% of the variation in our y value, range of motion after knee surgery, can be explained by the linear relationship between age and range of motion. That means that 30% of the differences I see from one patient to the next can be attributed simply to the impact that age has on the outcome of their surgery. Now, that means there's about 70% that can be due to other factors. It could be their surgeon, it could be their diet, their exercise, their fitness before we begin the surgery. But we are simply looking at how much of that impact does the X and Y relationship have on our Y value. So your job in interpreting R squared is understanding that approximately R% of the variation in Y can be explained by the linear relationship or the least squares regression line between X and Y. And certainly, we're always going to use the context of the problem. Now, when you do a least squares regression line, not only does your calculator give you your y hat equation, that it automatically will calculate r and r squared for you. Now, how do I calculate all of this information using my computer output? Well, let's take a look at this computer output here, and let's find the equation for the least squares regression line, y hat, and let's find the slope and the y-intercept. Well, remember, when we're looking at this data, the line that says constant is the line dealing with our y-intercept. This column here was our coefficient column. The coefficient in front of our x variable here is 0.8710, so that's slope. So our prediction equation is going to be 107.58, our constant, plus 0.8710 times x. Or this is going to be our range of motion, hat, equals 107.58 plus 8710 times h. Now, if you go back and look, we have an r square and an r square adjusted on our computer output. We never, ever pay attention to our r squared adjusted, but we do look at our r squared value of 30.6%. And then if we needed to calculate r, we could simply take the square root of r squared, or the square root of 0.306. Remember, the sign for r and the sign for slope are the same. My slope here is 0.8710 over 1. This means that approximately 0.8710, I think it was degrees of flex, we say there is an approximate increase of 0.8710 degrees of flex for each additional year of age. All right, the last thing that we need to talk about is we want to introduce the terms outlier and influential point in terms of bivariate data. We'll talk more about these next class. An outlier in a regression setting is a data point with a very large residual. A large residual or error means that data point falls outside of the pattern of the rest of my data, making it an outlier. If it falls outside the overall pattern of the other observations, we can simply call that point an outlier. The outlier can exist in the x direction, a horizontal outlier, or in the y direction, a vertical outlier, or it can be something that is both horizontally and vertically an outlier. Now, we also have another term. We know that if it falls outside of the overall pattern for our scatter plot, it's an outlier, but what is an influential point? An influential point is a point that influences where our line of best fit is located. That means if we remove the point, it would significantly change the slope of the least squares regression line. Typically, points that are outliers in the x direction are often influential points. These points sometimes have small residuals because they pull the least squares regression line towards themselves. The best way to check for an influential point, if we think we have one, is to remove it from the regression line and look at whether the new equation is significantly changed in terms of slope. We will talk specifically about outliers and influential points next class. So far, when we've studied bivariate data, we've talked about our least squares regression line, we've talked about our correlation coefficient and our coefficient of determination. Which of these measures are resistant to outliers? The answer is none. The least squares regression line, our r and r squared values are all greatly impacted by outliers. Shoot me any questions you have. Have a great day, guys. Bye-bye.